Hi, my name is Mikko Suvanto, and this is the MOSOMIC MEMS Microphone Guide. In this episode, I continue talking about MEMS microphone reliability. This one is about reliability in device production. Stay tuned! This series is sponsored by Innovating Technologies. The manufacturing process of the device into which the microphone is assembled can pose threats to the microphone. In many cases, the device manufacturing process isn't necessarily very well controlled. There are many variables that may affect the microphone reliability risks caused by the manufacturing of the device. Location of the factory may affect how well the OEM can monitor the manufacturing. Manufacturing facilities, for example, cleanliness and climate control. Production personnel, their know-how when it comes to handling MEMS microphones. And production equipment, for example, accuracy, age, and suitability for microphone handling. Also, the design of the device and its assembly processes can have a big impact on the safety of the microphones. The difficulty and complexity of the device assembly is a key factor. Also, all assembly procedures done near the microphones increase the risk of problems. It's very important that standard procedures and guidelines provided by the microphone supplier are followed. The microphone supplier typically knows what the microphone can take and what it can't, so their advice should be listened to. Of course, sometimes their requirements may be overly cautious because it's in the microphone manufacturer's best interest to minimize problems. Sometimes a compromise has to be made between increased device production cost and time and microphone safety. Microphones are typically tested at the end of the device assembly process to make sure they work like they should. Sometimes tests may be done also for sub-assemblies. The ability of the tests to reveal problems must be ensured. There's a wide variety of threats to microphones in device production. First of all, there are mechanical threats. Touching, poking, or other mechanical stresses can compromise the integrity of the microphone package or the microphone sensor. The sensor is in danger if something, for example sharp tweezers, are inserted into the sound port, or if the package is subjected to excessive mechanical deformations or forces. Also, the solder contacts under the microphone may be in danger if the microphone is poked. Microphone manufacturers don't typically specify any impact forces that would be allowed on the microphone. In other words, all impacts are forbidden. But the maximum mechanical pressure that can be applied on top of the microphone is often specified in the component datasheet. Second, the pick-and-place process may jeopardize top port components. In the pick-and-place process, the component is picked from its transportation package, typically a pocket in a tape that's carried on a reel, and placed onto the device circuit board. If the vacuum nozzle of a pick-and-place machine is used to pick up a top port microphone on top of the sound port, the sound sensor is exposed to a strong negative pressure shock that may damage it. Therefore, there must be a designated area for the nozzle of the pick-and-place machine on top of a top port microphone to minimize the chances of pickup being done on top of the sound port. There must also be enough safety margin between the pickup area and the sound port to take into account all tolerances that affect the accuracy of the pickup point. Nozzle dimension tolerances, nozzle placement in the pick-and-place machine, accuracy of the pick-and-place machine, microphone location in the tape and reel, and so on. The pickup area and recommendations for the vacuum nozzle dimensions should be specified in the microphone datasheet. Bottom port microphones are not in danger because the sound port is located safely under the microphone. The microphone may also be affected by contamination. The source for the contamination can be production facilities with compromised cleanliness, or, for example, circuit board routing, sawing that may be done near the microphone. There can also be other messy production procedures. Another threat for MEMS microphones is the cleaning of the device circuit board or an assembly. Common cleaning methods, such as pressurized air, wet cleaning and brushes, can all damage microphones. If pressurized air is applied directly onto the microphone and into the sound port, it can damage the sensor. Wet cleaning is a liquid contaminant that can affect the microphone negatively. The bristles of a brush can also poke into the sound port with dire consequences. It's important to acknowledge that, after assembly on a circuit board, bottom port microphones are exposed to threats such as contamination that originate on the other side of the board because of the sound channel that goes through the board. Excessive temperatures are another risk to be taken into account. The temperatures can rise too high, for example, if the reflow process of the device doesn't follow standards or if the process is poorly controlled. The microphone may be exposed to too high temperatures or mishandling, also if the microphone is reworked, meaning that a faulty component is replaced with a new one at some point after the reflow process. It should be noted that a microphone gets heated up also if the component next to it gets reworked. The allowed temperature profiles that the microphones are designed to withstand are given in microphone datasheets. Electrostatic discharges, ESD, are another significant threat microphones face in device production. Like I explained in episodes 9 and 21, the threat is twofold. The discharge can damage the microphone electrically or mechanically because of the pressure pulse caused by the rapid air expansion around the discharge. MEMS microphones are typically designed to withstand ESD. The immunity levels are given in microphone datasheets for maximum ESD voltage values that the pins of the microphone can withstand. Different values are given for discharges applied via air and in direct contact with the pads. The values vary also for different scenarios, such as a discharge that originates in a person versus a discharge coming from a piece of production machinery. Datasheets may also include ESD-related instructions. If not, you should ask your microphone supplier for advice. To minimize the risk for microphones and for other components, it's important to take the normal ESD precautions in device production. Good electrical grounding of the production machinery, ESD wristbands and ESD shoes worn by the production operators, conductive flooring in the facilities, ionized airflow systems over open trays and reels of microphones, and so on. These methods reduce the buildup of electrostatic charge in people as well as in machines. There are specific standards for the ESD handling of CMOS devices that are good rules to follow also in MEMS microphone production. I talked a bit about reflow and soldering already, but let's go into a bit more detail. The purpose of soldering is to connect the microphone onto the device circuit board electrically and mechanically. The principle with solder connections is to have matching contact pad patterns on the microphones and on the circuit board. To apply solder paste on the pads on the circuit board. Then place the microphone on the pads and run the whole circuit board with the microphone through a reflow process. The reflow process is done in an oven in which the solder material contained in the solder paste melts and adheres to the pads on the microphone and on the circuit board. The temperature profile that the boards are heated with in the oven is carefully designed to heat, melt and cool the solder connections in a controlled way. The profiles define the heating and cooling gradients as well as the maximum temperature that the microphones experience. The profiles typically follow IPC JEDEC standards. Microphones should be designed to withstand at least 3 soldering processes without significant impact on the reliability or performance of the component. Enduring more than one reflow is required because in many cases the circuit boards go through reflow twice, once for both sides of the board. For MEMS microphones, this is typically not a problem. The consumer electronics reflow profiles currently used are designed for lead-free solder that is less of a burden on the environment than solder with lead. The maximum temperature that microphones should face is 260 degrees Celsius, but in poorly controlled processes this may be exceeded significantly. Exceeding the specified maximum temperature is a reliability risk, so unnecessary thermal stress on the microphone, other components, as well as the circuit board should be avoided. The actual level of control on the reflow process and the temperatures that the microphone heats up to depend on the equipment and the skills of the personnel running the reflow process. The level of control depends also on the size, thickness and complexity of the circuit board, as well as the population density of the board and the sizes of the components on it. For example, heat propagation and distribution in a sprawling, flexible circuit board may be difficult to predict and control. Also, the temperature rise and fall gradients that the microphones face can vary significantly. Too fast heating may cause pressure buildup when the air inside the microphone expands quickly. In the worst case, this can cause the microphone package to disintegrate. This is the case especially for microphones in which the package is held together with solder connections that melt during the device board reflow. Packages held together by adhesives, such as epoxy, are typically less risky in reflow. Some device manufacturers have put protective tape on the sound ports of microphones to protect them from contamination during the manufacturing process. This is a bad idea, as the tape prevents the escaping of the expanding air inside the microphone, significantly increasing the risk of package disintegration. After reflow, the microphone should be let cool down in a controlled manner for 15 minutes. The reflow profile should take into account the type of solder paste that is used. A key parameter related to MEMS microphone reflow is moisture sensitivity level, MSL. It describes the tendency of a semiconductor component to absorb moisture from the ambient air into its structures and the tendency of the component to get damaged as a result of the moisture accumulation when it runs through the reflow process. Thereby, it determines the maximum amount of time a microphone or some other semiconductor component is allowed to sit in normal room conditions before it goes through the reflow process after it's been taken out of the protective moisture-controlled bag it's transported in. If a MEMS microphone is exposed to ambient air and humidity for too long before reflow, the component may get damaged in the reflow because of the moisture it has absorbed into the semiconductor structures. Therefore, it's important to know the properties of the component what comes to moisture buildup and the problems the moisture can cause in reflow. The moisture sensitivity levels of MEMS microphones are based on two IPC JEDEC standards. The moisture reflow sensitivity classification for non-hermetic solid-state surface mount devices, and the handling, packing, shipping and use of moisture reflow sensitive surface mount devices. A typical moisture sensitivity level for MEMS microphones is level 1. The higher the MSL of a microphone is, the stricter the requirements are on its exposure to ambient air and moisture before it goes into the reflow oven. A key acoustical and mechanical reliability factor in bottom port MEMS microphones is the sealing ring. It's the ring around the bottom port of the component that is soldered against a similar ring on the device circuit board. The soldering forms an acoustical seal between the microphone package and the device circuit board, enabling the formation of a leak-free acoustic channel that enables achieving high acoustical performance of the microphone system. Another function of the sealing ring is to be one of the soldered pads that adhere the microphone securely onto the circuit board. The reliability and quality of the soldering are optimized by applying just the right amount of solder paste onto the ring on the device circuit board before the microphone is assembled onto the ring. A too small amount of paste may leave gaps in the ring, leading to leaks in the sound channel. Too much solder paste may cause it to splash and end up in wrong places, even into the microphone sound channel, when the microphone is placed onto the circuit board by a high-speed pick-and-place machine. Too much paste can also cause solder bridging between the ring and adjacent solder pads, which can naturally cause problems for the whole system. Gas bubbles in the ring may cause leaks or weaken the mechanical integrity of the ring. Solder paste is applied on the circuit board and the pads by placing a stencil on the board and the pads, and then forcing solder paste through the holes in the stencil with a squeegee. The openings in the stencil match approximately the layout and sizes of the pads and soldering on the bottom of the microphone. For top-port microphones that have only regular contact pads on the bottom, the stencil design is simple. For bottom-port components, the stencil and solder paste application in general are a bit more complex because of the sealing ring. The amount of solder paste applied on each contact pad is regulated by adjusting the design of the stencil. The layouts, sizes and locations of the openings in the stencil, as well as the thickness of the stencil, are key variables. The bigger the hole is and the thicker the stencil is, the more solder paste will end up on the sealing ring. Guidelines for designing an optimal solder stencil and the land patterns on the circuit board are often given in microphone datasheets. Other key parameters for the solder paste application process are paste type, especially its particle size, as well as squeegee pressure and speed. Solder paste recommendations can sometimes be found in the microphone datasheet. The paste should be a no-clean flux type to avoid the need to clean the circuit board afterwards. Also, the sizes of the other contact pads on the bottom of the microphone, the minimum distance from one pad to the next one, and the amounts of solder paste applied on each pad must be designed appropriately to ensure reliable electrical contacts as well as reliable mechanical adhesion of the component to the circuit board. Choosing the right parameters reduces the risk of problems such as solder bridging or tombstoning, the phenomenon where the component sits at a tilt on the circuit board, or in a bad case flips onto its side due to a poorly balanced contact pad design. Okay, let's talk about reworking. It's the process of removing a component from the device circuit board and replacing it with a new one. This is typically done to replace a faulty component. A manual rework process, done for example with a soldering iron, can be a very uncontrolled and risky process in terms of the heat exposure of the microphone, the adjacent components on the circuit board, and the circuit board itself. The repeatability of the process is very questionable. Therefore, reworking should always be done with a rework station. The microphone is removed by heating the contact pads that hold the microphone to the circuit board so that they melt, and then picking the microphone up. An infrared workstation, if one is available, is often the best way to do reworking. It enables precise focusing of the heat to the right place. For manual reworking, thermal tweezers designed for surface-mounted component removal are a good tool. They heat up the component and solder joints and then grip and pick the microphone up when it's hot enough and ready to be removed. If an infrared station or thermal tweezers are not available and the heating must be done manually, the heating may have to be done by heating the board on the opposite side from the microphone so that the heat can be directed onto the solder pads. When the solder joints have melted and the component is loose, it can be picked off the board with tweezers. When removing the component, it should be gripped with tweezers from its bottom layer, the substrate plate, in order to avoid disintegration of the package. The removal should not be done with a hot air nozzle combined with a vacuum tool, because the focusing and spreading of the heat is very difficult to control. A hot air nozzle is basically a small hot air blower. The procedure for mounting a new microphone onto the circuit board is as follows. Solder paste is applied onto the contact pads either with a manually operated solder dispensing system or preferably with a stencil and a manual squeegee. Solder application accuracy is especially important with bottom port microphones. Accuracy ensures a well-sealed sealing ring around the sound port and helps avoid solder ending up in the sound port. A new component is placed on the circuit board with a surface mount placement machine. Manual placement is inaccurate and risky. The component is then reflowed, preferably with an infrared rework station. Using a suitable reflow profile with an appropriately slow heat ramp-up gradient, with a preheating phase, and a well-controlled maximum temperature is important. Again, a hot air rework nozzle should not be used for reflowing the new component in its place because of the poor controllability of the process. Just like in the case of a reflow oven, the sound port of the microphone should not be covered with tape or any other method during reworking. When reworking other components next to a MEMS microphone, it's important to make sure that the process is well controlled and excessive temperatures on the microphone are avoided. An infrared workstation is recommended also in this case to maximize temperature control and reworking repeatability. Again, the use of a hot air nozzle should be avoided. The use of heat shields to protect the microphone should be considered if poorly controlled heat sources are used for reworking components near the microphone. It's also important to make sure that adjacent components don't get overheated when a microphone is reworked. Damaging other components can be avoided by using well-controlled methods to apply the heat, and possibly by shielding the other components. For all reworking involving MEMS microphones, the personnel must be familiar with the requirements microphone set for heat application. Okay, that's it for this episode. The next 2 episodes will be about electroacoustic testing of MEMS microphones. Thanks for watching. I hope I'll see you around. Cheers. If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation.